Moroccan students in their group or in their laboratory.
So as I told you, now I don't have any laboratory here because
the question is for Professor Rahman.
I think I had one from, is it Tunisia, from Fethi Abdul Malik from Tunisia.
C'est le BOUDOUTI?
Fethi Abdul Malik from Tunisia.
C'est OK, c'est le BOUDOUTI. On commence.
Fethi Abdul Malik, and another one is a Salah Obaya from Egypt, Professor Salah Obaya.
Okay. So Professor Rahman, I think I have they asked me to start, and probably will. Are you okay for you? Yeah. Okay. So I will just give some words about your biography and so on. So c'est bon, je fais.
Yeah, I'm okay.
C'est bon. OK.
Okay, so ladies and gentlemen, dear colleagues, good morning. So first of all, I want to thank my colleagues from the University of Oujda, in particular Professor Hamouti and Touzan Fali, and all the colleagues, the organizers of this webinar conference. And I want to thank them for giving me the opportunity to be the chairman of this plenary conference of this morning. So I have a great pleasure to introduce Mr. Aziz Rahman, Professor of Photonics from the University of London, UK, who will deliver a conference entitled Design and Optimization of Silicon Nanophotonic Devices. So before giving him the floor, please allow me to give a short biography of Professor Rahman, which covers 40 years of experience in teaching and doing research. So Professor Rahman obtained his Bachelor of Science and Master of Science degree with distinctions from Bangladesh University of Engineering and Technology at the end of the 70s. And he obtained his PhD in electronics from the University College of London in 1982. And until 1988, he got a postdoctoral position at the same university. And from 2000 until now, he is a full professor at the University of London. So Mr. Rahman published more than 600 journal and conference papers, which have been cited more than 9,000 times with an Ash index of 43. He supervised 34 PhD students and received more than 14.5 million euro in research grants and projects. Professor Rahman is a life follow of E3Z and a fellow of the Optical Society of America and the SPI Photonics Society. So now I would like to turn the floor over to our colleague, Professor Rahman, to give his conference. So please, you have the floor, Professor Rahman.
Thanks for the kind introduction. Thanks for the opportunity. Thanks to Ahmed and all the colleagues at Morocco for this opportunity. Today I'll talk about an aspect of photonics, and which is coming up quite strongly is silicon photonics. I'll talk about silicon photonics. So the outline of my talk, I'll talk about briefly the emergence of photonics, and then I move to my talk, which is silicon photonics. My expertise has been mostly on the development of numerical methods, particularly finite element method, and their uses in waveguides and devices designs analysis. So I'll mostly focus on that. And then finally, I'll conclude. So photonics started or emerged in 1960s with the invention of semiconductor lasers and optical fiber. That was the start, and then it moved mostly on the communication side. That was the application. However, today, most of the invention, although came from telecommunication, but most of the market or the finance comes from the other, particularly appliances. All CD, DVD player are photonics. Most of all the phones, you have a display. All the laptop or computer, the display, they're all LCD, LED, organic LED, scanner, laser printer, LED for illumination. Most efficient light source is the LED. In the industrial use, metal processing, medical application, surgery, corneal sculpting, and lots of work on physical, chemical, and biological sensing. And because of that, it has so many applications that it enables other technology. And that's why EU has identified photonics as one of the 5 key enabling technologies. So now let's look back to electronics. We are all familiar with electronics. The electronics revolution started not with the invention of the valves and triode, which was at UCL, University College London, in 1904, but the real revolution came with the invention of transistor, which was 1947 in the Bell Lab. The reason the transistor was different than valves and triodes, that you can do the integration. And as you can do integration to make to small IC, later on move to LIC, VLSI. Now today, you can have a 10 billion, not million, 10 billion transistor in a 1-inch chip. And that's made the revolution. Prices started coming down, and almost everything is now enabled by the electronics. Now we are thinking that photonics, can it also enable, and what is its position? But what happens? The integration, what you have seen in transistor electronics, in photonics, this integration hasn't been that successful. And people are working on it, and that's why I'm thinking that why it has been so. The one reason is that material. Today is the material science conference, as you know. Unless you get a good material, you cannot have good waveguides or any devices. So to have we depend strongly on the material scientist and chemist. So the best waveguide, optical waveguide so far, is the silica, which has the lowest loss. Nothing is lower loss than this silica fiber in any communication system. The loss is 0.2 dB per kilometer. It's slightly less, even 0.1 around that time. The best laser, the first generation laser was gallium arsenide, but most of the communication lasers are indium phosphide. Most of the Blu-ray, DVD, maybe gallium nitride, they are compound semiconductor. Most of the modulators, the best modulators are still today is a lithium niobate, but it's never integrated. It's a totally different substrate. Base detector, G, yttrium garnet, iron garnet is one of the good isolator, and it hasn't been integrated yet. So the issue is that there hasn't been a single material which is good for, or reasonably good for, all these functions. And that's why integration has been poor. If you want a best waveguide, you go for silica. You want a best laser, you go for compound semiconductor. And that's why they have been all using different material. So discussion is going on. What about silicon? As you know, silicon is the best material for electronics. Whatever electronics you see today, whatever IC, VLSI, all from silicon. There has been heavy investment from the semiconductor industries. They have developed very, very highly developed CMOS foundries, very low cost, super precision. It is a wonder material for electronics. The question is, can it be used for photonics also? What are the limitations we have? So as you mentioned, it has very well developed CMOS processing facilities for electronics. So easily you can fabricate it as long as it is useful. So yes, we can do very compact waveguide. I'll show you some picture. Some of them are sub-micron dimension. The issue is that you can have a very compact band, less than 5 micron. Now, why compact band is important? Whenever you're integrating any components, hundreds of components, thousands of components on a single chip, you need to interconnect them. You need to connect a modulator with a laser, with an isolator, with a power splitter, everything you need to connect. If you cannot have a band sharper, you cannot put them closer. And you cannot put them closer, you cannot increase the functionality. And that's why by having a smaller band, it can allow more components in a chip, yield gets better, you can have more functionality, you get more reliable at a lower cost. And the beauty is that in the future, we can put both electronics and photonics, because if you use the silicon, silicon is good for electronics, and if you can make silicon good for photonics, then you can put both of them together, and that will be a revolution. So silicon so far, waveguides easily developed, has been done, directional coupler, power splitter, Prussian splitter, rotator, mode splitter, sensors, solar cells. These are all has been done well in our group. We have done lots of work on this. I'll show you some results. The issue has been remaining, the problem is coupler. Coupling has been an issue because it's a small dimension which is good for something, but it is difficult to couple to outside wall like optical fiber. Laser has been an issue because silicon is a indirect bandgap material. Modulator, there has been some reasonable progress, but still we want much faster modulator. So the research is going mostly on, although research are going on the other areas also, but also more on focus on the last three issues. Now my focus is how to solve them, how to optimize them, and so what are the numerical methods are necessary. Now numerical methods depends upon what type of device. If it's a two-dimensional approximation you can do, is a uniform waveguide. I'll show you the next slide what do I mean. If it's uniform in the Z direction, we call optical waveguide. Then what you need is a modal solution. You have to see what best modal solution is available. If the structure is a non-uniform, then it can be two types. It can be arbitrarily non-uniform. Then you need a beam propagation method. If it is some sort of coupling of few uniform section, then best approach would be to combine modal solution with junction analysis. It can be a three-dimensional resonating structure. Then you need a frequency domain approach. But there is another class of problem where you do need a time domain approaches. So the first one is optical waveguide. It is uniform in the Z direction. So the refractive index is a function of X and Y only. Its shape can be any shape, any complex shape. It can be any complex material. This material can be nonlinear, linear, isotropic, anisotropic, gradient index, diffuse, loss, gain, doesn't matter. As long as it is a function of X and Y only, independent of Z, then you need a modal solution only. In that, once you define your structure, what you want to find is a solution. And the solution means propagation constant. Most of the time we are interested in finding beta, but if the waveguide has a loss or gain, we need to also find alpha. And we need to find the field. It's a fully vectorial field. We need either E field or H field, because if I can get one of them from Maxwell equation, I can get the other. So my PhD, I started in 1979, and the major work we did, which this particular work has been cited more than 1,400 times. So it is a key development, and today all the software companies, all of them will use this magnetic field formulation. The reason is that that's the time I discussed and argued that it is a formulation where it naturally satisfies the boundary condition, which is a very important part for the finite element method. Now, if the structure is non-uniform, you have a uniform section, one waveguide on left and another on the right, but slightly misaligned. So it is not uniform at the junction. You have a directional coupler on the right. A single waveguide is launching to a directional coupler. There is a misalignment here. You have a single mode waveguide, a narrow waveguide at the bottom left, and coupled to a wider multi-mode guide. So what you can do modal solution on the left, modal solution on the right, but what happens at the junction? For the microwave people, it's called junction analysis method, which means that you need to find all the transmission and reflection and including the radiation modes at this junction to satisfy the boundary condition. What is the boundary condition? The fundamental boundary condition is at any dielectric junction is that tangential electric field and tangential magnetic field must be continuous. So this method I developed in 1988, so that it's called least square boundary cell method, so that continuity of the tangential electric field and continuity of the tangential magnetic field is enforced in this approach in a least square manner. And that paper has been cited 100 times plus. Then I had another PhD student from Egypt, Professor Salah Ubaya. He's now returned to Cairo. So what with him we developed is called BPM method. The first BPM method was developed by Fate and Flake in 1979, was Fourier-based and scalar. By that time, we have developed finite element-based techniques. We're also working on vector formulation. So the paper we presented in 2000, Journal of Light of Technology, is a FEM-based, fully vectorial, and also using PML boundary condition. Boundary condition is very, very critical for BPM and time domain approach. Less important, but not that critical for model solution. So people have used absorbing boundary condition, transferring boundary condition, perpendicular mass layer, and that is the most commonly used today. So that paper has been also cited nearly 150 times. So another approach is called finite difference time domain. Now this is the only one is a finite difference, not finite element. It is valid for general electromagnetic problem. It is very easy to code it, but is extremely computer intensive. The reason is that your FEM mode solver is a two-dimensional problem, BPM is a three-dimensional problem, X, Y, Z, and this is a four-dimensional problem, X, Y, Z, T. So if you don't need it, never use FTTD. But FTTD is a poor, because it's finite difference based, so poor in representing the finite structure, but still is a very widely used. We have tried to develop FE-based TD. We did some work, but still we need to do more work so that one day we can compete with FTTD. But today FTTD is more widely used time domain approach. So for photonic devices, what we have, we discussed the optical methods. We discussed model solution, junction analysis, beam propagation method, and time domain approaches. But also many optical devices exploits the light matter interaction. For modulator, it uses electro-optic model, electric field. For solitons, optical biostabile use a nonlinear model. For thermal tuning or VXR modeling, many places use thermal model. To design panda fiber, high-bay fiber, you need a stress model. For lasers, you need the gain model. And for Brunel scattering, SBS, you need light-sound interaction. A finite element can model not only that optical, but all the other physical model. And so that they can be combined in one package to have a very, very efficient interaction between these two models. So simplest one of the solution is silicon waveguide. Silicon waveguide, typically width is about 500 nanometer. I'm not talking micron. 500 nanometer means half a micron. Just think your hair is about 100 micron. This is less than 1/100th of your hair. Typical thickness is around 220 nanometer. 220 nanometer is very, very common. That's a mostly industrial standard. And this sub-micron structure can guide the light. And also I mentioned is a compact band, because on the side, you can use the low index. So you can have a very compact, less than 5 micron band in a silicon nanowire. Mode field, again, is quite strange sort of thing. Okay, this looks not that bad, but if you see that decaying and the slope in the X and Y direction can be different. These are the red vertical dash line are the interfaces. At this interface in one direction, you can see clearly there's a slope change, and these are due to the boundary condition. And if I see the electric field, which shows even strange behavior. Electric field in y-axis, EX, monotonically reducing, whereas electric EX along the X direction reduces in the core and then jumps in the cladding. In the cladding, you have a low index. Somehow it increases that. So it looks a bit contrary to Snell's law, but it is fact, and I'll show you the next equation why. And you can see in this slide that in the center, the field is lower than in the cladding. And that we published in 2010. The reason is there are lots of other things, but focus is here is that although H, all of them are continuous, but DN is continuous, but that makes En, normal component of electric field, not continuous. What does it mean? If some area En2, suppose in epsilon 2 is smaller, in an area suppose epsilon 2 is smaller, then En has to increase to satisfy this equation. And this is the beauty is used for some very, very exotic devices. I'll show you the next. But for that, obviously, there are lots of design issues we need to look at it. So this makes normal component of En higher where epsilon or refractive index is lower. That brings a novel design called silicon slot waveguide, where is the first time what you can see, the light is guiding in a void or low index area. It's like a bragg fiber sort of thing, but it's not. It doesn't need a periodicity. It's just a single interface. It allows a region with a high power for sensing application, or it can be filled up with a polymer, highly electropic polymer, to have a better high-speed modulator in silicon, which is an issue now today, to get a better modulator in silicon. It can also have a silicon photonics like SBS, and as I said, it can be useful for sensing. The reason is the low index area can be air, can be water, where you can have a higher field. And if you can try to sense something in the air or water or that surface, it gives an extremely top quality sensor. So we looked at the design of some called horizontal slot. There are slot can be vertical or horizontal. If it is horizontal, it only supports TM mode. If the slot is vertical, it only supports TE mode. So we looked at the design of a horizontal slot. We looked at the fabrication process. And then we looked at the optimization. And what you can see that as you change the core height, and we are talking about 0.17 micron, that is 170 nanometer, and then you get the best response when the DNA changes from ssDNA to dsDNA. And that's how you can optimize your sensor design. There is a plasmonic is another exciting thing in photonics. If you have a simple plasmonic, like a planar plasmonic, the solution is very simple. You can have a transcendental equation. However, if I have a plasmonic structure where width is comparable to the thickness, the solution is very, very complex. And I haven't seen any other groups publishing a solution for this sort of complex structure. We published in JLT, Journal of Light of Technology, and showing that there are modes which is like a mode at that upper interface and the lower interface couples to have an even-like or odd-like modes. A mode on this left interface and right interface couples to have a odd-like or even-like mode. So there's a lots of different sort of modes can form in this structure. And so it's very, very complex mode there. Now in the slot, there's another exotic slot. Instead of high index dielectric, you can use a metal either on the top or in the lower. And that's known as the plasmonic slot. And we looked at the many device design, like in this particular case, using the porous zinc oxide for gas sensing application. You have a Mach-Zehnder, one is the reference arm, one is the sensing arm. In the sensing arm, what we have done is a porous zinc oxide, and that can, any gas passing through that, absorb there selectively, changing the refractive index, changes the phase, and changes the output power. And this one we published, Journal of Light of Technology 2017, and this figure clearly shows beautiful plasmonic peaks at the metal dielectric interface. Another thing is you need in all optical device called power splitter. How compact you can design a power splitter. And in most of optical design, MMI base is mostly compact design. And so this one showing a 3 micron wide multimode section, only about 17, 18 micron width. You can work as a nicely power splitter 1/4. This is showing evolution of the mode, the interference there, and at a certain distance, it makes 4 clean, nice, clean picture 1/4 splitter. Device length is only 17 micron. However, silicon is highly polarization dependent because index contrast is very high. And so what we looked at is the next one, after 10 years later, that how we can design a power splitter which is polarization independent. If I put a metal there, then metal influences the TM mode and it doesn't influence TE mode much. But metal also brings the material loss. So what we put a silica buffer layer to control the loss, so that by having a reasonable acceptable loss and also a properties where we can control the effective index of both T mode shown on the upper 4 line and the TM shown by the lower 4, you can see the TE mode, the blue one is the without metal and the red with metal. It changes, it is small, whereas the TM mode, the changes from the lower blue to middle red is significant. Now I have shown 2 modes here. The reason is that device length is critically depends between the delta beta of the first and the second mode. And that's why we need to see the condition for the delta beta, is it met or not. And once we've done that, then that we published 2016 showing that both T mode and TM mode, you can see the nicely interference coming, and it's coming 1/2 at the distance is about 20 micron. So what we have is here is a polarization independent power splitter. But sometimes you need asymmetrical power splitter. It's not 1/2 or 1/4, but suppose 10% and 90%. Now, what you can do, you can have a simple design like a splitter, which is 1/10. Once it's divided 1/10, one of them is a 10%, I can let it go. But other 9, I can recombine into another combiner by 9/1. Looks simple, but slightly problem. The reason is that whenever it is dividing into 1/10, each of them magnitude is 10%, correct? But they have a different phase. They follow a particular phase pattern. A combiner need a specific phase pattern, and these two doesn't match. And because they do not match, so you need to add the required phase for each of the ports. So that means you have a 1/10 splitter. 9 of them, you take them, add the right phase difference, and then combine, and then you get a right output. Then we look at a simple design where instead of that, if you have a slightly angle, and we realize an angle of 1 or 2 degrees cannot satisfy the phase exactly, but can satisfy the phase roughly, approximately. So we look at the design. So this one is with the angle 1.2 degree, and you can see 10% and 90%. And this is with a phase in between this waveguide, and this 10% is going this side, and 90% power is here. That we published in Quantum Electronics 2018. These days, one new thing is coming, it's called mode division multiplexing. As the demand for the communication is getting higher, wavelength division multiplexing are being used for the last 20 years. New concept is coming for mode division multiplexer. Now for that, one component you need is called mode splitter. That means if you have a waveguide with many modes there, I need to split H111, 21, 31 separately. The way we can do that, we can have a waveguide of directional coupler of different non-identical, asymmetrical, so the width of the 2 waveguides are different, but in such a way, the propagation velocity of H111 and HY31, suppose, are identical. If you can make them identical, only then power can transfer from one mode to another. It has to be called phase matched. And that we design, and that we look at the simulation, propagation tolerance, and that we published IEEE 2016. For polarization diversity application, we will use polarization controller, but for integrated optics, you need more advanced component. The 2 things critically need is called polarization splitter and polarization rotator. And also another called polarization controller. So simple design polarization splitter can be that if I can control the coupling length for TE and TM and the device length such that one is M times and N times, one is odd and even, then I can split them. It's a very simple approach we can think. And that we work for many publications we did. One of the recent one was using a multi-layer silicon waveguide and looking at the mode here. And this is showing that TE mode is from the left waveguide coupling to the right, whereas another one is coupling to the right and coming back. So at the output section, T is in the right and TM is on the left, so they are splitted. So at the input section, both T and TM can be in the left guide, but in the output, T and TM is coming out of two different ports, and that's called power splitter, pollution splitter. We have been working on a pollution rotator for more than 20 years. Early design we did called multi-stage design. That was one of the best those days. We also used something single-stage design. In that case, we used this like weight etching approach, and for that was work in a gallium indium phosphide. That particular design we did for Plessy. More recent work we are doing on a silicon. In a silicon waveguide, what you have a two waveguides, one nanowire, one a vertical slot. You design in such a way that TM mode of the nanowire is a phase matched with a T mode of the vertical slot. And if you can do that, then if you input the TM mode, it will couple to the vertical slot as a T mode, and not only the coupling, it converts the pollution state. And that's the one we're showing is here again, nanowire and the vertical slot. And this is showing a particularly T mode coupling to the nanowire becoming a TM mode. That we published 2013. One of the recent work we did for a resonator, but instead of ring resonator, we looked at the straight resonator, so the bending loss can be less. But for this one, we had to develop a new computer code because the three-dimensional structure, and we can see the mode fill, like here is the slot waveguide. So we're exploiting the slot technique and also the straight resonator innovation for this sensor design. And then we looked at the cavity mode. In that is a cavity mode, and we're looking at the different slot with a filled and empty, how the sensitivity of the resonating wavelength shift, and that we published in IEEE Selected Topics Quantum Electronics Journal. As I mentioned, coupling to the outside world is a problem, silicon, because silicon has a spot size of 0.2 micrometer square, but a single mode fiber is a much big 80 micrometer square. As an electrical engineer, if you know, if you couple two different impedance, there's a mismatch. Same way as an optical engineer, if you couple two waveguide with a different spot size, there's a mismatch. And here, if you couple, only 4% power is coupled, not lost. 4% is coupled, 96% is lost. So the likely solution today, most of the people use Bragg grating, is a off-axis grating, highly frequency wavelength dependent. Also, loss is around 5 dB. So what we designed a structure, single nanowire. This is it's called spot size converter. We have a nanowire on the top is a multi-layered structure, wider to expand the field horizontally, multi-layer to expand the field vertically, so that they expand to a bigger one, and then coupled to a fiber much easier. Next slide is showing the field profile. We're looking at the phase matching, and once we do the phase matching, we look at that how we can get the maximum expansion, and at that time, the field you look like is like that. It's not like a Gaussian shape. It is a bit Gaussian on the horizontally, but multi-layered structure. However, still coupling is significantly better. And if I see that if I don't use that multi-layered structure, the coupling was only 3.9%. If I use the 11-layer structure as shown, coupling increased from 3.9% to 56%. So loss has reduced from 14 dB to 2.7 dB. But instead of using to fiber, if I couple to a lens fiber with a small radius, coupling loss reduced from 2.7 to 0.3 dB. Recently, we did another work where we did called pollution independent design. So where it is T couple, little tapered, then phase match to TM, then here expanded TM, then this is polarization splitter, so that TM couples here, but T doesn't come, and what you have got both T and TM. That we published recently in Scientific Report. We have been working for nonlinear photonics for a long time, even for second harmonic generation. We worked in 1997, a student from Ghana. Then we had a student from another country, gallium arsenide, zinc oxide, 4-wave mixing. But recently we have been working quite a lot called supercontinuum generation. And we published Optic Express 14, 15, quantum electronics, JOSA, many papers, and the paper has been cited more than 230 times. We are also working on called light sound interaction, called nonlinear, called SBS. And again, we published Optic Express, Applied Optics, Quantum Electronics, and the mode shape in acoustic waveguide. Optical waveguide is guiding the sound. And you can see the mode shape, this is the sound wave. It's quite a strange sort of shape you get. And that now we are looking also more advanced. Like this is a slot and grating and is a acoustic and light. So we're looking at the acoustic mode in a slot gratings. This work we did with a group in Shanghai Jiaotong, and this is showing acoustic mode. And also another interesting thing is coming. If you know SBS, is that the principle is electrorestriction. However, when the dimension is very small, the radiation pressure has more effect than electrorestriction. You can see this is log scale on the left. You can see that in the red dot, radiation pressure is higher than the electrorestriction. So in any SBS for a very small structure, you cannot ignore the radiation pressure because that is higher than electrorestriction. We are also working on a called SBS based switches. It is a well-known phase change material, and some of you, my friend today, are from the electrical engineering for solar cells, energy storage. You know that in a solar cell, you can store the energy in a battery, but there are lots of people who are working instead of battery using a called latent heat-based power storage. That energy storage, they're using GST. But obviously in our work, we use GST as an optical switches. So we look at the GST, we model it, and the group in Shanghai Jiaotong University, they have fabricated many of these devices. And then we published one of the earlier paper in IEEE, cited by 70 times. But more recent paper, we published in High Impact Science Bulletin, Impact Factor 9.5, ACS Photonics, Impact Factor 6.88. We published some new papers in 2020. We are also working on a solar cell group. We are working in a solar cell, as you know, the efficiency, even if you can increase the efficiency by 1%, then can make a big difference. We recently published in Optics Express, and what we have is a nanowire textured solar cell with a little offset, a hole, and that can increase the current, short circuit current from 23 to say 27. Even suppose few percent increase can be a significant improvement as long as the cost doesn't increase much. That's the important thing. So you can increase the efficiency, and also we look at the okay. So here we are saying that to the energy world, how we can make more efficiently electricity. But another thing is we need to see the last slide. We have to see that how we can save consumption. Global data center consumes 416,000 gigawatt. That's today 3% of the world electricity consumption. In another 10 years' time, this one will increase significantly. Now, obviously, it's a big power, but where is the power is going? Strangely, 50–60% of the power, it goes just spent in the gold wire. The gold wire is connecting the data in the memory to processor, processor to processor. That's fine gold wire consumes that. So the research is now ongoing. So the silicon nanowire can connect the intra-chip data transfer. And also by having the same, if we can have the same electronics and photonics in the same chip, then we don't need to transfer the data outside. In the same chip, we can process both electronic and optical part. And that's why we can save the electricity consumed. Oh, I think the last slide, it didn't come. So I think thanks for listening to me. Thanks for all the Ahmed and others for inviting me. And thanks for listening to me.
Okay, so very much, Rahman, for this nice conference. Very, very interesting about the utilization of silicon in nanophotonics devices. So now we will give the floor to our PhD students and our colleagues, to ask their questions. So please, if you have any question, probably I will start with Professor Innawi, Si Ahmed.
Okay, thank you very much. I'm very honored. And I want to thank first Professor Rahman from the University of London. He introduced this topic, photonic, to this conference, which is very important. And I would like, I'm not an expert in photonic, but since photovoltaic and photonic material science are not far from each other, I have some very general questions, so I will not go to the small details. So I think the photonic is very important for Industry 4.0, for the faster communication, and there are water sensors and pollution sensors. The first question is, do you have any activities in your group on this topic? That's one thing. The second questions or comment or discussion I would like to put in this conference is, when you design your sensor from material into device, do you think that one has to think about hardware and software? Because if you have a sensor in any application, there is it's a hardware, but you have also a software for the communication to transfer data from the measurement into the computer, etc. Do you think one has to think from the beginning about a kind of business plan for the design? And the third thing, what I would like to discuss with you, but maybe we can do it with mail afterward. I worked in the last part of my career on micro design for solar cell. This means we start in a project called Sheta project to make small solar cell with micro solar cell, which can bring enough power compared to a large area, just by designing small solar cell, what we call micro design, and to use 3,000 sun, 3,000 times 1,000 watt per square meter in order to gain in space. I send one publication in the chat of this conference. So that is all general question what I would like to put. If you can comment on this.
Yeah. Okay. Thanks. Okay. Thanks. I'll do a few. So one thing is a sensor. We have a big project with a very big project, £500,000 project, designing of a optical sensor to detect heavy metal in water. Heavy metal means like a mercury, cadmium, lead, and this we are using. These are the experimental one. We have a facilities in our lab to fabricate the fiber bright grating, long periodic grating. Then we functionalize those grating with a special material, which if in water, if you have a lead compound, it absorbs there, or if you have a mercury compound, it absorbs there. If you design for a lead, it will not absorb mercury or anything else, so that it is selected. And then it changes the refractive index. Then we measure it. the light output, how it is changing with the wavelength. And these are the experimental one we have in the lab we are working. And some of the design, if it is on a silicon design, then obviously we have to design it. Silicon, most of the fabrication we did in China, but not at City. But fiber-based design, we can fabricate. So yes, we have a work on water quality sensing, same way it can be used for gas sensing. We are looking at a very new project, which is called PFAS. There is a called a material, is a pollution material, which is very, very sort of coming dangerously for Europe. We're trying to work on that. And I think my screen went black. I don't know whether you can see, but you can hear me probably. You can hear me?
I hear very good.
Okay, because my screen is black now because I was not changing the cursor, but at least I can hear you, you can hear me.
Yes.
So at least we can ask. And then you're looking at some solar cell design. We'll be happy to look at some of them because we are good in numerical design. And like one of, as I said, my ex-PhD student, he's a professor, Salah Obaya in Egypt. He's working more on a textured solar cell. So he's working on that. And then that's, yeah, roughly some of the things you mentioned. We haven't done anything COVID, but one thing we noticed that this PFAS in the water, that there is a news that it reduces the effectiveness of any vaccine. You have the COVID vaccine, but COVID vaccine is effectiveness will reduce if somebody has a like a PFAS in their blood. And so that's why PFAS is coming quite strongly as a sensor.
Yes. Yes.
Okay, thank you. Is there any other question?
From my side, it's fine.
Okay, thank you. Other colleagues or professors, is there any other question, please?
Can I have one, Professor BOUDOUTI?
Yes, Professor Tuzani.
Okay.
Go ahead. Yes.
Thank you so much, Professor Rahman, for this nice conference.
Thanks for listening.
In the same meeting, we have Professor Sa'doun from Qadi Iyad University. He emphasized about the presence of the oxygen in the batteries, like you are using silicium oxide, SeO2. That means sometimes the presence of oxygen in the batteries can have a burn and some accidents. Yeah, do you have any idea about safety of your photonic systems? That means in the real experience.
Yeah, photonics is normally, we always say is safer. The reason is in photonics, we don't use electricity. As example, that if you have a suppose sensor in a coal mine, a sensor in a oil field, if there is a gas and methane builds it up, and if you have an electrical sensor, and when you switch on and off a sensor, there can be little spark. If you have a sensor in a coal mine, then it can cause an explosion if it is an electrical sensor. But optical sensor will never do that because optical sensor doesn't use electricity. Okay, you may use electricity somewhere behind to make the laser to light, but within the fiber, within the sensor, we don't use any electricity at all. And that's why it is much more safer, but also it is much more rugged. Silica is one of the most rugged material. We tested our sensor in the corrosive water of a Sydney sewage, in the drain in Sydney. And if you put a electrical sensor to detect pH and other thing in a drain water in Sydney, and electrical sensor after 3-4 months, it gets corroded. If you put optical sensor in a Sydney drain water, it doesn't corrode because it's so. If you see optical sensor from the corrosion point of view, safer. From the electrical point of view, it is safer. And also, like lots of places, like a radiation effect, you can have a sensor where it is like in a nuclear reactor. and also it stand by high temperature. So it is generally is much more safer optical sensors.
Okay, thank you, Professor Aziz Rahman. So is there any other question, please, from the audience?
Maybe I can ask a question, if possible.
Yes, please.
Thank you very much. Thank you, Professor, for this very nice talk. I would like maybe to continue this problem with electricity, because of course your sensors don't need any electricity because they are optical ones, but maybe some voltage could tune the properties of these sensors, of these devices, via electrostriction effect, also maybe the change of refractive index after applying voltage to some doped silicon and something like that. Just please comment about this. Maybe it is not important in your field, but I, for example, deal with magnetostriction, and I know that, that it's a good way to change something inside the device. Thank you.
Yeah, but that we use like a magnetostriction or electro-optic, like when you design a modulator, and lithium light modulator, you have to use an electric field to modulate the light. If you want to design a panda fiber or highly bifurcated fiber, you need to bring the pressure, so that there is an electro-optic effect is exploited. Same with the magneto-optic devices. So if it's a device which utilizes the electric field or magnetic field or stress, that obviously you're using it. But if you think of a sensor, if it's a sensor you want to detect a magnetic field, then what you're looking, you are not designing, but you are looking at a material which can change the refractive index in the presence of a magnetic field. So you are detecting that, and you are not bringing any electricity to do that, but suppose somehow the magnetic field is there or electric field is there.
Good idea.
Your optical device is purely optical, okay? And it only changes the refractive index in the presence of that electric field or magnetic field, because the material in the sensor, you might have used as a gyrotropic or electro-optic material, and then your design is fully optical. But as I said, that electro-optic modulator, yes, there is electrodes are there, and because you are modulating a laser light, you are not sensing, not for sensing, but for a device application.
Thank you very much. It's very amazing. Thank you.
Okay, thank you, Professor Tadouz. So now, is there any other questions, please?
Yes.
Yes,
first of all, thank you, Professor Aziz Rahman, for this very interesting lecture. And my first question is how to control the thickness of the silicon layer. And the second, what are the elements to be added as doping to improve or reorient the nature of the device or sensor?
Yeah, silicon devices are really, really accurate. When they say the thickness is about 220 nanometer, it is within few nanometer probably, because this technology has developed by the electronics people, and they have been working, with trillions of pounds they're investing in the development of their computer memories and computer CPU. And we are only using them. So silicon photonics is very, very accurate. Although when you say that when you want to, particularly thickness is very accurate. When you're looking at the width of a guide, a typical design, we want 500 nanometer, that is half a micron. It can vary about, say, 5% width. It can vary. So when I ask my PhD student to design a device, then we tell them, look, somebody's designing at a 500 nanometer, but it may come up at 495. If you design it and then put that change in the width as a 495 or 505, and see whether your design will still work or not. So for most of the design, we look at the effect of the fabrication tolerance, the tolerance we do expect from the practical fabrication. So because if you cannot make within the, like, suppose you design a device which is very critical with the fabrication tolerance, then it is not a practical device then. But thickness is very, very well controlled by the deposition technique.
Thank you.
Okay, thank you very much. Now I will give the floor to Professor Sadoun from Marrakech.
I don't know if you hear me, yeah?
Yes, we hear you. Ask your question.
Thank you. Thank you, Si Hussein. Thank you, Professor Rahman, for this presentation. I'm sorry, I'm somehow far from the topic, but I saw in one slide that you are using some film as thermal energy storage.
Yeah.
Or is there any real application, or is this just potential application? Because I guess that your materials are a little bit costly.
My design, I just mentioned that we use in a design in a GST. That's a phase change material, and that we use for optical design. We are not using for electrical storage. We are using for optical switches, and we have published very, very top high impact journal like a science bulletin journal, Impact Factor 9+. So that is a practical device for optical networking. But the reason I mentioned that what I noticed as I was looking at it like a solar cell, I realized that a lot of people are working on energy storage for the solar cell system. And typical people, low-cost system people use a battery, but battery is not that efficient. So lots of research is going on use of latent heat as a material change from A to B. When you change the temperature, the heat changes. But when you change the state from one state to another, that latent heat is much bigger. So you can have a much higher power heat storage instead of just changing temperature, but if you can change the state of the material. And GST is a material. Lots of people are considering GST to use as a thermal storage for the solar cell. So there is a very, very exciting work is going on.
Yeah.
But those people are thermal people, so I'm not familiar with their work, but I've noticed that they're using it.
But I'm not expert, but I think that for the PCM material, you need to have some lower melting temperature. And in your case, I guess that such intermetallic materials melt at very, very high temperature.
This is typically around 300 to 600 degrees centigrade.
Oh, okay, that's enough. That's enough. Thank you. Thank you.
If you see GST, because GST is used in an optical disc, in a CD DVD, it is used there. But obviously, in a CD DVD is used as a data storage, and what we are using is as a controlling the optical switching. But you are looking at because solar cell people are looking at not at a data storage, but as a heat storage. But if you look at, I think you can see some nice paper, and probably you will understand it better than me because I'm not a thermal expert, but probably you will be able to see that. And there's a good research is going on, use of GST material to exploit its latent heat, to store the latent heat for the solar cell energy storage, so that in the daytime, you convert to one state, in the night, you reverse the state to get back the heat and then use it.
Okay, thank you. Thank you.
Okay, thank you, Professor Sadoun and Professor Rahman Aziz. So I have one question, if you allow me, the audience. So Professor Rahman, as I understand, you are expert in the numerical calculation from the beginning of your thesis, as I understand from your presentation. Yeah. And now there is a lot of experiments and applications of this kind of wavegates. It's really interesting. I mean, I understand a lot of things from your conference, and as I understand now at this moment, our PhD students are using this commercial software to make the calculation, like console multiphysics. I think, yeah. So now they don't know what is the boundary conditions and what is going on and all these things. So they are using this software and they get the results. And sometimes it's not easy and it's not obvious to understand the results. So this is just to say that the finite element method is very interesting from the utilization point of view, but it's not easy for our PhD students to understand what is going on inside these waveguides and in these boundary conditions and in these bands and so on. So my question, Professor Rahman, is about the utilization of this demultiplexer in telecommunications. So we have published one paper. Just it will be published in 2021. I mean, it was published in lecture notes in electrical engineering. It's about the utilization of one wavegate at the entrance and two wavegates at the output. And on these two outputs, we make resonators. So we use plasmonic, insulator with metallic materials. So we can use this Y-shaped demultiplexer with one entrance and two outputs, and on each output we make resonators and we filter one frequency. So it was a numerical calculation, and I want to ask you if it is possible in your laboratory to make this kind of experiments. So
yeah, no, we have like very limited. From the numerical side, I can do a range of devices, waveguide, where there's a lithium niobate, silicon, anything. But from the experimental side, we have only facilities for optical fiber based. So we can do like a fiber grating, tapered fiber, nanofiber, long periodic grating, and then sensor from that, we can do that. Yeah. But for silicon one, like we have a good collaboration with the Shanghai Jiaotong. They have excellent facilities. They can make silicon devices. So the design, whatever the collaboration we do with them, then they fabricate it. So similarly, if you have a collaboration with other universities, they do. So as I said, our own facilities is limited. For 40 years, I've been working on numerical method. That's I'm very strong. But as I said, yes, for COMSOL is very good code. In our time, we didn't have the code, but these are based on our work, what we have done. It's very good. But when the structure gets very, very complex and complicated, the students need to understand that any solution coming out of it, if the structure is simple, but complicated structure, a plasmonic structure, as you said, that is a magneto-optic material. Is the formulation valid for magneto-optic material? You know, is the field, has they taken the enough boundary and those sort of things? Is the result converges or not? I always ask students to check the convergence of the result, because if you're running 10 times and the different 10 mesh results are different, which one do I take? You know, so you have to look at the convergence of the results. You have to look at any mode you get, any effective index you get. You always plot the field. See that whether field confined or not. You know.
Yes.
So that's the thing we always tell our students.
Yeah. Thank you. I have a second question, please, about where you are using this strip and slot Bragg structures. Yes.
Yeah, that one was done. Was done in China.
Yeah, we are talking about light and sound.
Yeah.
But we are working also on this kind of systems, which we called phosonic structures. They are phononic and photonic at the same time. So my question, I mean, are you studying also this, what you call this interaction, light and sound, on this kind of structure? Yes.
Yeah, we're looking at light and sound interaction. That's true, because what we find the acoustic mode in this optical waveguide.
Yeah.
And we find the optical mode in this optical waveguide.
Yes.
And we look at the overlap integral, or called SBS. So at the moment, mostly we do, like you can see some of the acoustic paper we have published. We did some small amount of interaction, but objective is that to have that like a more. We did some work, as that we have done at least how many 3 PhD students work on acoustics and optic interaction. Obviously, you want to continue that. So, so these are like, we take optical waveguide, find the acoustic mode, and then find the optical mode.
Yeah, yeah.
And then we find the overlap between the optical and acoustic mode.
My last question, Professor Rahman, is about the utilization of graphene with silicon. So in this last time, we are making, one monolayer of graphene between silicon, and we obtain very, very interesting, results, because the graphene, for example, from the phononic and from the plasmonic point of view, we can have these large gaps by using this graphene, for example. So please, could you give us some ideas about the utilization of graphene? And the last question is about the energy storage. If we are working also on this, what we call this perfect absorption materials. Materials which they are not reflecting, not transmitting, but they capture all this incident wave we launched on, and we can transform this kind of energy, what we call the perfect absorption materials, like the black hole or something, something like that. So please, could you give some words about graphene and this perfect absorption materials? Thank you.
Yeah. So the perfectly absorption material, sometimes you can call it a metamaterial. The lots of our group are working on that metamaterial in Southampton and other places. And obviously, I haven't worked on it, but I was planning to think that if I can use that PCM for metamaterial, then you can control that absorptions of that surface, metasurface. So it can be a one step even ahead of that. So you can have a surface where it's a perfectly absorber, but also you can switch on and off by using a phase change material. For the graphene, one of my PhD students did PhD on a graphene. We haven't published anything yet, so we have worked on that. So obviously, a single layer about 0.3 nanometer thick, and then it has the very, very strong confinement of the light. So again, it's a very, very exciting material, and lots of groups are working on graphene-based photonics also. So it is like the work you're doing as a graphene or metamaterial, they're very, very exciting work.
Thank you very much. Thank you very much. Is there any other question from the audience, please?
Maybe I have one.
Yes, please. Yes.
I would like, first of all, to join myself to my colleagues to thank you for your, Professor Aziz, for your kind presentation. Thanks. I have one question. During your presentation, you talk about top-down method to prepare your devices.
Which one?
To prepare your devices, use, top-down method.
Top-down method?
Yes. Like lithography and so on, to prepare your devices, yes? What about to use bottom-up means to use nanoparticles or plasmonic nanoparticles to prepare your devices? Please, could you give us an overview about the use of this kind of material to prepare these devices?
Like I'm not that much of experimental expert, but obviously there are groups are working with a nanoparticle. And I think Professor Ahmed was telling Hafed Talib in France. I think he's a nanomaterial expert. So they are more expert on the fabrication side. But what we do the simulation of using this nanoparticle on the devices. So suppose that you have a optical sensor, you deposit the nanoparticle, zinc oxide nanoparticle, or the metal nanoparticle, and then they have a selectivity. and then it changes the refractive index. So we look at the simulation side of that we have looked at it. Fabrication side, some of the devices have been fabricated. Some sensor has been fabricated in Malaysia, in University of Malaya. They do fabricate it. Some of the metal oxide has been done. So I haven't done the fabrication myself personally, but the colleagues have done it. But we have done lots of simulation on the gold nanoparticle or zinc oxide nanoparticle simulation we have done.
Okay, thank you.
I have, if you allowed me, I have a question.
Yes, Professor. Yes.
Yes. Okay. By the way, Abdel Hafid Talib, he's the one he asked you about the top down. So he's the guy.
Oh, okay. He's the one asked.
Yes.
He's the expert, and I didn't know to get the name. He's the expert.
Okay. My questions go in the same way, but it's a little bit for fundamental understanding of quantum mechanics. It's the future for the sensor, maybe. So what do you think if you lower the size of the sensor in order to see the confinement of electron and to see some quantum size effect? Do you think it's possible, this kind of research?
We haven't done, because what happens that I always focus on optical side, not on quantum side. So the minimum device size, sometimes I work on a plasmonic, and sometimes the thickness can be, say, 20-30 nanometers. But again, I didn't look at the quantum state sort of thing. I looked at because my focus has been always on Maxwell equation, from the confinement of the light. That has been my focus all my life. So I have worked on a 30 nanometer size thickness of metal layer, but I never looked at the quantum side. But these are the things like we can think of the future, because if we work on the project, we hope, or if not, something else, we can look at the possibilities. I haven't worked on quantum side yet.
Okay, thank you. Thank you.
But if you can make a comment on this. Yes, Professor Nawi, it is true that if you have nanoparticles, we have this electron confinement because your nanoparticles are smaller than the mid-3 parts of the electron. So we can have plasma, which is very sensitive to the absorption of any gas on the surface of these nanoparticles or molecules. Because these gas or molecules can have a donor or an electron donor or acceptor, and then it will change the plasmon of the nanoparticles.
Yeah, we look at the plasmonic resonance, but we look at the plasmonic resonance from the material model. So we look at the different material model. We take the refractive index as a function of the wavelength.
Yeah.
And then we look at the plasmonic resonance.
Yeah.
So that we have done, but not on the quantum set. But obviously, plasmonic resonance, we are working all the time.
Okay.
Yeah. Thank you very much. So please, just one probably stupid question. I mean, can we speak about the interaction between electrons and photons in this kind of silicon structure?
Electrons and photons, because if you see the lasers are electron and photon interaction. I haven't worked that much on active devices, but those people who work on some modulator, they call carrier depletion or carrier enhancement modulation. They do work on the carrier side. So those are carrier electrons and holes. I haven't done that because the modulator I worked on mostly on electro-optic modulator. So, but as I said, but again, for all the laser model, you have to do both optical and electronic model together.
Yeah. I suppose that in this case we have to use the quantum mechanics. I mean, with what is called electrodynamics. I mean, we have to use both of models. I mean, quantum mechanics and Maxwell equations.
Because I haven't done the detail, because I haven't done the laser modeling. But obviously, what I do know that they do solve those Laplace and Poisson's equation, and from that quantum, because they are analyzing the quantum layers, and they're looking at the carrier dynamics. And once you get the carrier dynamics, then the carrier gives you a carrier related the gain and absorption. Then that part is optical. People then fix it up. So there is a model. Simple Laplace will not work, because it is a much more like a quantum mechanical layer.
Okay, thank you very much. Is there any other question, please, from the audience? Probably one last question, if you allow me, Professor Rahman, is I did not understand very well when you are using these multi-layers to increase the percentage from 4% to 56% to go to the fiber. I did not understand well this design.
The works like that. If I have a one waveguide which is suppose half a micron wide and say 220 nanometer thick, the mode is very, very small. If I can couple to another waveguide which is instead of half a micron wide, if it is suppose 6 micron wide, if I can couple, the condition for coupling that you have to make their same beta or same phase. Suppose I can design. If I can design it, then the light can couple from a narrower half a micron guide to a wider 6 micron guide. Then you can couple it better. But remember, you expanded the mode only horizontally. Now, if I make two similar 6 micron wide guide, two similar, and then the light then from one wider 6 micron guide, it couples to the second one. But before coupling to second one, when it's coupling 50-50, then you have a mode which is half in the lower 6 micron guide and another half is the upper 6 micron guide. So now the light is expanded a bit vertically also. So now instead of 2 layer, if I have 11 layer, and if I think of a directional coupler multi-layer guide, I can design a condition when the field will expand also vertically. So now, if I can expand the field horizontally by taking wider guide and vertically by taking multi-layer guide, then I expanded the field both vertically and horizontally. And that's how now it matches better with the fiber profile. Okay?
No, the layer structure is playing the role of a resonator, which makes the connection between the principal waveguide and the fiber, more efficient, as I understand.
Yeah, so once it is expanded and the field at the right position, when the field is expanded because it's a mode, they start interfering couple. At the right position, the field is expanded both horizontally and vertically. Now, if you do it called butt coupling, if you bring a fiber exactly opposite to that section, multi-layer section, then that's called butt coupling. It will couple nicely. For practical purpose, you might have to use an index matching layer in between. But then, and that's the way people will work.
Thank you very much. Really, really very interesting conference. For me, it was really very, very interesting. And with this Mach Zehnder interferometers and so on and so forth, it's very, very interesting. So please, is there any other question?
Yeah, thanks for lots of interaction. I'm very happy that at least we have a very, very useful discussion with many, many friends and colleagues.
Thank you. You are welcome, Professor Rahman.
Thank you, Professor Azizur Rahman. Thank you, Professor Hussain Boudouti. Thank you for all, and welcome to next conference at 3 o'clock Moroccan time with Professor Taduz from Poland.
Okay, we will be there. Thank you very much.
Thank you.
Okay, thanks to all of you. Yeah, thanks.
So be safe and good day.
Okay, thanks.
Thank you, Professor.
Thank you. Bye-bye.
Professor.
Thanks.
Yes. Have a nice day. Professor Leo, thank you.